The constraint propagation engine is a subsystem responsible for iteratively narrowing variable domains through the application of constraint rules. The engine maintains a queue of pending constraints and processes them in order of insertion. Each constraint contains references to one or more variables and defines the legal combinations of values those variables may simultaneously hold. Processing a constraint performs forward elimination, removing values from affected variable domains that violate the constraint. The core propagation loop continues until a fixed point is reached, meaning no additional domain reduction occurs in a complete pass through the constraint queue. Each processed constraint is placed at the end of the queue if the domain of any of its variables has been modified. If no modifications occur during a full iteration, the propagation terminates. This ensures consistency across all constraint relationships without redundant computation. Variable domains are stored as immutable bit sets when cardinality is low, and as sorted interval sets when domains are sparse. The bit set representation supports efficient intersection and complement operations required by many constraint types. Interval sets reduce memory overhead for continuous or near-continuous domains. Domain state is never modified in place. Instead, new domain objects are allocated and previous references are replaced atomically. The constraint queue is implemented as a circular buffer with a write position and a read position. When constraints are added during propagation, they are appended to the write position. The read position advances through the buffer in order. If the read position catches the write position, a fixed point has been reached and propagation halts. The buffer capacity is pre-allocated and does not dynamically resize during execution. Constraint types are defined through an abstract interface with a single required method, reduce. The reduce method accepts the current variable domains and returns a tuple containing the new reduced domains for all variables in the constraint scope. If no reduction is possible, the method returns the input domains unchanged. Common constraint types include equality, inequality, arithmetic relations, and cardinality constraints. The equality constraint maintains that two or more variables must hold identical values. Its reduce method computes the intersection of all input domains and applies this intersection to all variables. If the intersection is empty, the constraint is unsatisfiable. The engine detects this condition and signals a conflict to the calling solver, which may then trigger backtracking or constraint relaxation depending on the solver's strategy. The arithmetic relation constraint defines a mathematical function between variables, such as x plus y equals z. The reduce method uses interval arithmetic to compute the feasible range for each variable given the ranges of the others. For the constraint x plus y equals z with x in 1, 5, y in 2, 3, the feasible range for z becomes 3, 8. Each variable domain is intersected with its computed range. Conflict detection occurs when any variable domain becomes empty during reduction. When a constraint's reduce method returns an empty domain for any variable, the propagation engine immediately halts queue processing and returns a conflict indicator to the caller. The conflict includes a reference to the constraint that triggered it and the set of variables that became infeasible. This information guides conflict analysis and backtracking algorithms. Constraint priority is managed implicitly through insertion order rather than explicit priority values. Constraints are processed in a breadth-first manner as they appear in the queue. This avoids the overhead of priority queue operations and ensures predictable execution order. If specific constraints must be processed before others, the caller must insert them in the desired order before beginning propagation. The cardinality constraint enforces that exactly n variables from a set must hold values from a given subset. The reduce method identifies which variables cannot possibly satisfy the constraint and removes values accordingly. For instance, if a cardinality constraint requires exactly 2 variables to be true from a set of 5, and 3 variables have already been assigned false, the remaining 2 must both be true. Lazy evaluation of constraints is supported through the optional query method. A constraint may define a query method that evaluates the current state without modifying domains. This allows the solver to check constraint satisfaction or feasibility without triggering propagation. The query method is useful for monitoring constraint status during search or for implementing optimized solver heuristics without imposing unnecessary computation. Memory management for domains employs reference counting to enable safe garbage collection. When a domain is replaced by a newer version, the old domain's reference count is decremented. Domains are deallocated when their reference count reaches 0. This approach avoids explicit memory tracking by the caller and ensures that stale domains are reclaimed promptly. Snapshot capability allows the engine state to be captured at any point during propagation. A snapshot records the current variable domains and the position within the constraint queue. The captured state can be restored later, allowing the solver to undo propagation and explore alternative branches. Snapshots are themselves reference counted and deallocated when no longer referenced. The inequality constraint enforces that variables must hold different values. For binary variables, reduce identifies when one variable has been assigned and removes that value from the other domain. For multi-valued domains, reduce computes the set of values that would violate the constraint given current assignments. All different constraints generalize this to enforce pairwise equality across an arbitrary set. Statistics and diagnostics are collected during propagation without overhead. The engine tracks the number of constraints processed, the total domain reductions, and the propagation time. These metrics are available after propagation completes and may be logged or analyzed for performance tuning. High reduction counts on early constraints suggest redundancy that could be optimized. Integration with external solvers occurs through a standard interface. The propagation engine is initialized with a variable set and constraint collection, then executed by calling the propagate method. The method returns either a success status with the propagated domains or a conflict status with conflict information. Solvers call propagate repeatedly as part of their search strategy, capturing snapshots before trying different assignments.